Hi 242. So in this video and the next video, we're just going to be working through some examples using this technique for integration by substitution that we presented in our last video. So remember, this one is useful for changing the variable and for handling some integrals that we don't immediately know how to find the antiderivative of. Something that it's beneficial to notice is that this technique is really useful for finding antiderivatives of expressions that have been the result of composition, right? This integration by substitution is reversing the chain rule, right? So that's probably beneficial for us to write down, right? So substitution reverses the chain rule, right? And remember that chain rule is useful for finding the derivative of functions that have been formed by composition, right? Remember, you might want to recall this for just a quick second, right? The chain rule is when you have composition of functions like this. Oops. There we go. Parenthesis, parenthesis, bracket. There we go. The chain rule says you do derivative of the outside, leave the inside alone, times derivative of the inside, right? Okay, so this is the chain rule, right? And remember, it takes derivatives of functions defined by composition, right? Well, this technique for substitution reverses this, right? So anytime you see in your integral a function which has composition apparent, right? When you can see that there's been a composition that's been performed, there's an expression living inside of another expression. Substitution is probably a great thing to try, right? So you can kind of think about this if you want to write sort of how substitution works, right? Remember, substitution is going to reverse this process. So if the derivative moves this way, right, substitution is going to move it backwards, right? So substitution would be the reverse process, to go backwards, right? So if you want to write that using an integral, because that's what we're doing, is reversing this process, then you could write that the integral of the right side here, oops, here we go, g prime. The integral of the right side has to be the original starting thing, right? F of g of x. Okay? And again, maybe there's some sort of constant of integration, a real number that was living in the definition for this function before you took its derivative. But remember, working backwards, we're not aware if there was a real number living there or not. So we have to sort of assume that perhaps there might have been one and put this big plus c right there, just to remind ourselves that there could have been a real number living there that we didn't know about. Okay? So again, this process for integration by substitution is reversing the chain rule, okay? So anytime we have an integrand which appears to have been produced by a composition of some kind, there's an expression living in another expression, maybe, then substitution is going to be a good candidate, a good thing to try, right? So let's maybe try another example here. Let's try something that looks like this. Okay, let's try, how about this one? Okay. All right, so let's see. I do see the same situation we had last time, right, where there's something living inside of some parentheses being raised to a power, right? There's also this other thing living here, right? This other 6x squared living here. But notice if we turn back a page, right? If we're ever trying to reverse the process of the chain rule, right, notice that usually what we'll end up having is some sort of derivative, and then there's like this thing plugged in, right, and then there's the derivative of the inside stuff, right? So the chain rule sometimes will produce this, always produces this derivative of the inside stuff here. And if you notice, that's exactly what we have right here, right? Notice that this thing right here is the derivative of the inside, right? So what that means is that using substitution would be a great technique to try here because we have a derivative which was produced using the chain rule, right? And substitution reverses the chain rule. Okay, so remember that when we do this process of substitution, we have to choose a u, right? That's the whole point, is we have to choose a u, and choose a u that simplifies the integrand, removes the trouble spot, okay? For us, notice that the trouble spot, remember, is this stuff living inside of here, right? So let's let u equal that stuff. Okay, If that's our choice for u, remember that our next step is to rewrite the entire integral so that it's only written in terms of u's and du, right? Okay, so remember we get the du by taking the derivative of this u expression, right? So that means that here du dx is, I just write the derivative here, which is 6x squared. Okay, notice that if I move the dx up there with the 6x squared, I get du equals 6x squared dx. And notice that's exactly what is living here at the end. 6x squared dx is in fact du. So now when I start rewriting this integral, right, when I sort of say bring this down and rewrite it, yeah, this integral is going to be what? This stuff inside is just u, so this is u to the 20th. And this last stuff over here is what? All of that is just du. And now how much easier is that integral to do than the one up here, right? Because notice it says the variable is u, so this is just a power of u. We do that integral by reversing the power rule, so u to the 21st over 21, plus my constant of integration, don't forget that, okay? But now it's important to remember that I can't leave it written like this, right? Because our original variable was x, and our final answer should be in that same variable. It should be written in the same variable. Okay, so what we end up doing is saying, okay, if it's supposed to be u to the 21st over 21, don't forget that u is written as 2x to the third minus 3. So let's just replace that u with its expression of x, and we'll be done. Okay, so it says all of u to the 21st, so that means all of this 2x to the third minus 3 raised to the 21st power. So I need parentheses, right? So 2x to the third minus 3 to the 21st over, oops, over on the outside, over 21 plus c. Okay, and now that's considered complete, right? So if you don't believe me that that's the antiderivative, how can you check? Remember, to check to see if you have the right antiderivative, you can take the derivative of this answer and you will get the integrand in here. And I suggest that you do that check as yourself. Perhaps pause the video right now and just try that. Make sure that you take the derivative of this final answer here and you get the integrand here. Okay, so let's try another one, right? Because we're just going to keep doing examples. The best way to see these is to do examples. Okay, what I can do before we do the next one is give you a couple of hints, right? So here are some good choices for you. Okay, some good places to look for your choice for u, for your substitution. Okay, insides of parentheses, we've already seen that inside of parentheses is a great place to select a u, right? That's the location of a trouble spot when things are yucky inside of the parentheses being raised to a power or something. Okay, another good place is in denominators. Maybe there's some yucky expression living in a denominator. That would be a good choice. Another good place to pick is up in the exponent of an exponential, right? Up in the exponent of e or something like that. That's a good place to pick a u substitution. And lastly is inside of a radical. Okay, living inside a radical, if you have some sort of crazy expression in terms of x or something living in there, then that's a good place for a substitution. Okay, so let's try another one. Let's try something like this. How about x squared? How about 1 over 4 plus x squared times 2x dx? Okay. And they'll start out fairly straightforward, and then they'll get a little more complicated, right? So according to my suggestions, notice for my hints for good places for you, there's no parentheses in this problem, but there is a denominator, right? Okay, and so perhaps we should choose that denominator as our choice for u. Okay, and I'll go back up so that you can see the method too. Okay, so let's let u equal 4 plus x squared. Okay, remember the next step here is to rewrite the whole integral, and that means I have to replace that dx and that x over there, but I first need to see how to relate dx to du. So I do that by taking the derivative of this expression of u. So du over dx, right? Du dx, the derivative is, what's the derivative of this thing? 2x. Okay, but notice that that allows me to write du equals 2x dx. Aha! And if you look, 2x dx's are right there, right? So when I now rewrite this integral, I get integral 1 over, what is 4 plus x squared? That's u. Don't forget that's u, right? That was our choice. Times 2x dx is just du. Great. All right. Is this an integral we know how to do? The variable is u. The integral, or the function we want to find the antiderivative of is 1 over u. We know the antiderivative of 1 over u. That's ln absolute value of u, right? ln absolute value of u plus a constant of integration. Okay? Last step, we're not done. Remember, you got to get rid of that u. You want to make sure that your final answer is written in the same variable as the original problem. So we got to write this back in terms of x. So that means this is ln absolute value of, what was u again? U was 4 plus x squared. Plus our constant of integration, of course. Okay? Great. So that one was pretty fun, I think, right? Okay, let's try another one. Again, lots and lots of examples. Remember, if you need a break, you can always pause the video, come back and watch examples later, or you can go try some practice problems on your own or something like that. Let's try something like this. How about x squared plus 1? Okay. So remember, one of my suggestions for choosing your u is to look inside of a radical, right? Notice there's a radical living right here, yeah? So perhaps a good choice for you would be to choose the stuff inside the radical. Perhaps it's a bad choice. You know what? If it's a bad choice, then our work will just get messier and messier and messier, and it won't turn out like, it won't simplify down to something we know the antiderivative of, and maybe we can just erase it and try something else. Okay, so for our suggestion here, let's try u, which is, let's try the inside stuff, x squared plus 1. Okay, again, when I'm at this point, I now need to say, well, I'm going to need du, so I better find du dx. Okay, so I need to see how du and dx are related. Okay, so they're related via the derivative of u, so that's 2x. Okay, usually we bring that dx up, so I have du equals 2x dx. Okay, and in the last example, we had exactly this expression here in our integral, but I don't see it. Do you? I don't see a 2x dx. I see that we have, let's see, maybe use a different color. All this stuff in here, this is all u, right? So what I've got left is actually these two pieces here, right? I've got x dx left over. I know 2x dx is equal to du. So doesn't that mean then that du over 2 is equal to x dx? Yep, it does, because I just divide both sides by 2. So x dx is equal to du over 2, right? Okay, so let's start rewriting things. Let's start replacing things. Okay, so let's rewrite down here. So this is equal to the integral of, let's see, x dx is du over 2, okay? So I'm just going to leave that x there for a second. Well, I'm not even going to rewrite it because I know it's going to go away with the dx in a second. I'm going to put that du over 2 at the end. Okay, so inside of the radical, I just have u, because that was our choice. And x dx is du over 2. Okay, remember that that 2 is living in the denominator, right? That means I could pull that out as a 1/2 out front. So I can write this, integral. And how can I write the square root of u? That's u to the 1/2 du. Okay, great. Well, I can now do that integral, right? I know what the antiderivative of u to the 1/2 is, so let's go to our next page here. So this is, let's see, we have, what do we have? 1/2 integral u to the 1/2 du. And the antiderivative of that is 1/2 out front as a constant. So reverse the power rule. I add 1 to this power. 1/2 plus 1 is 3/2 over the new power, 3/2. And of course I need to include my constant of integration. Okay? That 3/2 can be flipped and multiplied out front, so it would be 1/2 times, what would that be, 2/3, right? Because that would flip up and be a 2/3, u to the 3/2 plus c. And of course that simplifies even a little more because now the 2's cancel. So I'm left with 1/3 u to the 3/2 plus c. This is not our final answer because it's still written in terms of u. Okay, so I need to make sure, oops, that I go back here and remember what our u was. Go back one page. What was our u? It was x squared plus 1. Okay, so if it's x squared plus 1, go ahead and put that thing back in there for u, and that'll be our final answer. 1/3 x squared plus 1 to the 3/2 plus some sort of constant of integration, because some kind of real number, right? Again, that was our u there. Okay, so our final answer is 1/3 x squared plus 1 to the 3/2 plus c. Okay, again, pause the video at this point and check to be sure that that works. In the next video, I'll do a couple more examples for you.